In this lesson, we're going to look closely at resistance and see what causes resistance. First of all, let's have a look at this very simple circuit here. I've just got a 9-volt battery and I'm connecting it with an electric cable. Now, you should never do this, and we'll see why in a minute, but let's supposing that I close the switch. What will happen immediately is that an electric current will flow around that circuit from the positive terminal to the negative terminal. But what we're going to say here is there is always something that opposes the flow of an electric current. And the thing that opposes that current is called resistance. Resistance is the opposition to the flow of electric current in a circuit. Now we can represent this simple circuit here by the circuit diagram on the left. So we'll close the switch, and the resistance in this circuit is represented by a symbol which is a rectangular box. So this is the circuit symbol for resistance, and the equation symbol is the letter R, it's a capital R, and the unit for resistance is called the ohm, symbol omega. So the resistance in this cable that is opposing the flow of electric current is represented by this symbol here. Now, what happens as I increase the resistance in a circuit? So as the resistance increases, what happens to the current? So if I measure the current by inserting an ammeter in series with the resistance, then as the resistance increases, we will see that the current decreases. So the current is inversely proportional to the resistance. Make the resistance bigger, the current flowing decreases. Reduce the resistance and the current flowing through the circuit increases. But what actually causes resistance? Now, there are a number of factors that we're going to look at in this lesson and in the next lesson. But the first factor is actually in the material itself. It's an intrinsic factor that depends on the nature of the material, which is nearly always a metal. Now, we remind ourselves that the particles or the atoms in a metal are arranged in a lattice structure like this, and interspersed around these atoms are what we call free electrons. Now, in a conductor there are plenty of these free electrons, and these are free to move through the lattice. Let's just draw them now. So this is our metal lattice, these are our free electrons. And so when the switch is closed, these free electrons will start to pass around the circuit. Now, conventionally, the current flows from positive to negative. In reality, in fact, the electrons are flowing in the opposite direction. I don't really want you to worry about that now. So what's happening is that the free electrons are flowing around the circuit, and as they do so, they pass through the lattice like this. And as they pass through the lattice, what will happen is that they will start to collide with the ions in the metal lattice, and they will be sent in different directions. In other words, the ions in the lattice will impose the movement of these electrons as they flow around the circuit. Let's just do that again. So one of the factors that will affect the flow of these electrons is the nature of the lattice itself. Some metal lattices will oppose the electrons, the free electrons, more than others, and as a result some metals will have more resistance than others. Now, as these electrons flow through and collide with the ions in the metal lattice, they will produce heat. It's a little bit like when you rub your hands together on a cold winter's morning, you generate heat. Well, the same sort of thing happens here. These electrons will collide with the metal lattice and they will produce heat. So we're generating heat. And this is an important thing when we're considering resistance. Whenever an electric current flows around a circuit and encounters resistance, then heat will be generated. And the reason why I said you should never really do this is because you will probably generate quite a lot of heat if you connect a cable directly to the terminals of a battery. So not only will the wire heat up, which could be quite dangerous. But because quite a large current will flow around the circuit, then you will also discharge your battery rather quickly. So to resume what we've just said, the resistance in a conductor depends on the nature of the material itself. Now some materials, say really some metals, are able to produce more free electrons than others. As a result, they are better conductors and offer less resistance. In addition, some metals, as we've just mentioned, their lattice structure itself will oppose the passage of free electrons less than others. So some materials or metals will offer less opposition. So these metals that produce more free electrons and whose lattices, that's to say whose lattice structure offers less opposition to the movement of those electrons, will be better conductors and will produce less resistance. So in the previous unit, when we were talking about insulators and conductors, we made a general statement that metals are good conductors. But here we're learning that although most metals are good conductors, some will be better than others due to their internal structure and the number of free electrons that they produce. For example, silver is a better conductor than copper, which is a better conductor than gold, which is a better conductor than aluminium, which is a better conductor than iron.